Hello. So today we're going to learn the algorithms on C++. Yes, today is 24th November. So let's start. And this class is really interesting because this algorithm really is the British transversal search, which is the BFS, and it's used to find paths. It's used to find things about social network, about GPS, and a lot of things. So it's really interesting. Let's see why this algorithm is so interesting. The algorithm, and so I've put these drawings here so the algorithm that use graph. Graph is just a number, just nodes and vertices to build interesting things here. The definition. The algorithm BFS finds the order, the search in which elements are disposed from each other. So, for example, this is the first layer transversally. If we put a horizontal line here, 0 and 1 will appear first, and after 2 and 3. So the algorithm is going to catch these layers, right? Maybe not so well drawn like this, right? Let's continue. So what the algorithm does, we will discuss in just a moment. But first, I'm gonna give and of course in the algorithm, we could not put 1 here. We had to put 0, 1, 2, right? So if there are v vertices, we have to begin from 0, 1 till n minus 1, because each vertex is represented as the value of actually it's represented as edges. So this is the edge 0, 1, this is the edge 1, 2, this is the edge 2, 3, and so on. There is no value for these things here, just the number of the vertices. So here are 2 exercises I recommend you to do. But first, so there are 6 people using phones. In such a way, there are just 2 connections available for each one. I'm just giving an example of how you can use the BFS to solve problems. So we find the order in which the layers are disposed, and the following exercise I recommend you to do. So let's go and see how it really works, this algorithm that's based on graph. So here, first of all, we have the simple one. That's the most simple. A kind of problem could be the letter A, right? So indeed, we have to find, right? Oh, sorry. We have to find the queue and the visited. But what are these 2 things? First of all, this 0 to 1 represents an edge, right? An edge is formed by 2 vertices, in this case here. And in this case, the edge is 0, 1. And 0 has 2 edges, 0, 1 and 0, 2. 1 doesn't have an edge because I'm considering edge as directed. And so there is no arrow going back to 0. So there is no edge of 1, neither 2. But it could have an arrow, yes, of course. So Q is just a list to take the visited and to print, and the visited is just an array, an array of the values that we have visited, in which, of course, we will use a bool to represent the values that we're talking about. So let's continue here. And the program is in the side gigs for gigs. So first of all, we represent this graph, right? This graph here in this following way. We give the number of vertices. We use we use a pointer, adj to list. So it will point to the elements of this list. We have a constructor that will receive, in this case here, the vertices. We will initialize v with v, and we'll also, for each element, for each vertex, there will be an adjacent element. For example, 0. 0 has 2 adjacent elements. So actually, we are allocating dynamic memory for this ADJ because this is an array of lists. And so for each v, for example, 0 has a list, 1 has another list, 2 has another list. So for each of them, there is a adjacent list, right? And so we will use it in just a moment. And after we have public methods, right? A function, right? As it follows, this edge is the v to w edge. For example, v would be 0 and w would be 1, so it's 0, 1 edge. It could be 0 to 2, which is 0 to 2. And so this, well, to add an edge, this is another function, a function of the class graph. So that receives two parameters to build the graph, to build the edge, I'm sorry. And the ADJ, which is a list, we will put these elements to the back of the list. For example, the adjacent of 0 will have to receive the 1, for example, and this will be going to the back, right, of our list. And the BFS will receive this int as a parameter and will return nothing as no other function here. And we need, for example, to put, right, we have a visited. This array, in this case, it's a pointer, right? So we will have to allocate, it's a pointer to bool, indeed. So we have to allocate dynamic memory, new bool of the number of vertices. And for each vertex, we will have, so it will be, for example, for n, we have 0 to n minus 1. In this case, n minus 1 here in the maximum. And so it will go from 0 to n minus 1. In this case, v minus 1. And for each value, we'll put if it was or not visited. First of all, no one was visited, so we put everything to false, right? So visited of 0 is false, visited of 1 is false, and visited of 2 is false. We create a queue for BFS, a queue that will just be a list of the vertices conform when we go from each one of them. So, for example, there is just the creation of a list. We mark the current node, right? We mark the current node as visited, and we enqueue it. So, for example, if this is 0, we will put it true because we have visited 0, and we'll put back in the queue the 0. So this 0 will be in the back of our list. So we can just begin here. Every one of them is false, so 0, 0, 0 in this case here. And all right, because this is a bool, so it's in this case it's false, false, false. And I will be used to get all adjacent vertices of a vertex. So we will use an iterator. This iterator is a pointer to the beginning and the end of our adjacent. Adjacent is of type list. So let's begin. While our queue is not empty, indeed our queue has the element 0, so it's not empty. So we dequeue a vertex from the queue and print it. What does that mean? Let's see. S equals q dot front. So yeah, indeed here it's in the front of the queue. We put it S to be in the front of the queue. So we see out the S and we q dot pop front. So we take the 0 here, and for all adjacent vertices of the dequeued list of the dequeued vertex S, if a adjacent has not been visited, for example, 1 and 2 were not visited, then what we do, we mark just visited, right? So this was visited, we know that. And of course, this 2 and 1 will be visited right now here, because this puts to the begin. So adjacent, the first adjacent is this one here, and the second adjacent is this one here. This will be a 0 in the iteration process, and this will be a 1 here. But what we're talking about is not about position of iterators. We're talking about the value. Indeed, this value here, because star I returns a value, and this is just the address. No, actually the position. This is what we are talking about, the value. So the value of star I will just be the position of the one in the visited list, as we know. It will be just this position because it has begun with 0, 1, 2. So in this case, as it's 1, it corresponds exactly to the one in the queue. So the queue will receive, we have deleted the 0, now we have the 1 because we have visited the for example, 1 was not visited, right? So what we do, we just visit if the 1 was not visited, so it will be visited. So we're putting 1 here, it was 0, and after we q dot push back, or let's do it a little bit more carefully for you to understand better. So in the case of 1 was not visited, so we are doing true for 1, right? Or it the same thing as 1. In the other case, we do push back 1, so 1. And we have, for example, now the 2, because now the iterator is 1, but 1 is just the position in terms of lists. We're not talking about lists, we're talking about visited. So visited of 1 is actually 2, right? In this case here, it's actually we're talking about the second. I'm sorry, we're talking about the second, so it's really 2. And we just put 1 here and we put 1 here because we're push backing the another number, which is 2 here in this case. So this is the example for the solution. And of course we needed to add the edges, so we add the first one 0 to 1, and of course we have to add the edge of 0 2. So if we begin by 0, the first and second layer will be printed respectively in this order. All right, what's strange? All right, so 0, 1, 2. So we print the first layer and the second layer. Here's the first layer, and this is the second layer. And I hope you understand what, abstractly, what does that mean. There are many algorithms that use this method. So the second one is this one here. So how can we implement this one here? The same way as the other. We just go to the 0, we put, let's go again. We just put the 0 here first in the queue, and everything is put to 0 because there are 4 vertices. And the first one, so let's go here. So here is 1, and we take because here is saying that we have to push back the 0, right? And we put it to true in this part here. And it's not empty or queue. It will be empty just at the end. So in the previous exercise, it would be empty for everything. So as we have put to the front in right here, the queue, we pop front after we have printed. So we just take it. And for the adjacent vertices, we know that the adjacent of 0 is 1. It's only 1 because the directed arrow is just pointing to 1. So this is a directed graph. So in this case, we're talking about the adjacent, which in this case is 1. And what we do, if visited, not visited, 1 was not visited yet, right? So we put it to true. So true. And we put 1 to the back of the queue because queues are put in the back and took by the front. So pretty simple. And the rest, I think you understood clearly, right? So we can build this for this, in this case, to build the edges. It's just for us to 0 actually no, 1 goes to 2, and this other case here, and 2 goes to 3 in this order, and 3 goes to 0. Okay, all right. If we execute the code beginning by 0, we could have begun by any other vertex. The order will be 0, 1, 2, 3. Actually, like a group in mathematics, abstract algebra. All right, it doesn't matter, I think. So, and the solution for this exercise that we were talking about is very straightforward, right? It's quite straightforward. And so for this exercise here, what we need really to do is just to build this graph here. All right, we could have just built this graph here, and this is the solution that we were talking about. This is the graph. Very interesting symbol, right? And so we just do the proceedings that we were doing. This is very useful algorithm, right? Let's go back again to the procedure in which we do this algorithm. We have to, there are just 5 things in the graph: the vertex, the number of vertices, the list, right? A pointer to list. This is a group. How can I say? An array of lists, and for each list is an adjacent collection of vertices that are adjacent or near the vertex that we're considering. And so this is there are 5 things: this list, this function to add the edges, and this to print, of course, the BFS algorithm. And there are a constructor that just receives v, right? Because we're accessing the class, we can use a special modifier here. And the new list, which is a collection of v lists that begin from 0 to v minus 1. And for each list is the adjacent collection of vertices, adjacent from the vertex that we're considering here. Very interesting. And here we just push back we're just at the edges, nothing very much special here. And so this is our understanding of the thing, and I hope you do that, you understood that. And so let's go to the applications. And what are the applications for these things, right? Actually, the applications are very straightforward, right? So we understood how to do this problem, right? Because each one can just, all right, I think we forgot something in the problem that we're talking about. There are 6 people using phones such a way there are just 2 connections available for each one. So actually each connection can have 2 edges. So indeed we needed to have put more 1 edge from 0 to 1 and 1 to 0, from 1 to 3 and from 3 to 1. So actually it's not correct the way it's drawn. So we would have to put for each edge for each connection 2 edges, because we can send the signal and the signal can go back to us, of course. So for each one we would need to put 2. So it would be 6 times 2, 12 edges for 6 connections. All right, let's go. Interesting. So applications, let's go to the very interesting part, the minimum path between nodes. So we could see that it really is the minimum path between nodes. In each of the cases, we would have a sequence of these things here, and the sequence would really be put in a sequence order. So 0, 1, 2, or 0, 2, 1, but actually 0 from 1 and 2 the same distance. 0 to 3 is bigger than, actually we're talking about the distance. 0 to 3 is bigger than 0 to 1. So actually it's quite, and yeah, GPS system. GPS system use this kind of method of going from to find places where we are near. So it uses this system, right, as we could understand, because actually there is a very interesting story about it. Actually, because the inventor of this algorithm was, I'm not wrong, I think was a German called Kuse, Konrad Kuse, and it was the his thesis. He had created the first computer, programmable computer, and after it happened that his thesis built in his language was rejected. And many years later, I think 25 years later or 27, his program, right, his software was developed again, I think, by the the man that created the finite machines of Moore, mathematician. So actually, his thesis, if was not rejected, we would have faster probably algorithms, right? And he, uh, thanks to him, people that download torrents in the internet can do that very easily from seeds. And I do just know these names, of course, because I have learned about it, not because I do that. Or it doesn't mean that I don't do that, but you understood that. So there are the seeds, which are the people that upload the contents, and the others, of course, download, right? And people that download at the same time are called leechers. And the people that download one at a time, it's called just, of course, are called peers. So there is this path between nodes, and the more the people have downloading, more the people gets faster the connection between these sequences, because it's a graph. IP protocol, each IP internet protocol is used for internet communication. So people can have a number, I think, of 9 digits or eight, right? And so each number is represented as a protocol. And indeed, so Pentagon has many data if you're worried about internet history, and that is in the cache, right? Even the hidden mode. Actually, Pentagon has these informations. I don't want to scare anyone. Um, Friend-to-friend networks. This is a method that we have described the minimum path of the nodes. There are, of course, more advanced algorithms that we're not talking here, but we will be talking later in another episode. In social network uses, of course, it's a very interesting application. Every user is a node that has many connections given by edges. So zero, for example, zero is a person that knows 1, 2, 3, 4. So there are edges from 0 to 1, 2, 3, 4, and the algorithms to find this are is the BFS, a very very important algorithm that was rejected as a doctoral thesis. So that was the PhD thesis. So actually, that was all for today, and see you in the next episode.